So it is every physicist's goal to discover fundamental laws of the universe. And arguably one of the most important laws in the whole of physics is F is equal to ma, which is Newton's second law. This law is a law on which the whole of classical mechanics rests. It has stood the test of the quantum revolution, special and general theories of relativity. Welcome to my advanced physics class, where we discuss modern physics and classical physics. We are looking at the various applications of this beautiful equation we see on the board, F is equal to ma. The first of the applications, we are looking at what we call the conical pendulum, which is a system of a string attached to a mass, whirled in a horizontal circle, and at each point in time, when you take a snapshot of the system, the string makes an angle theta with a vertical. The string has a tension T, and of course gravitational pull mg, given that the mass of the bob is m. Now the supposed radius of the circle is r, and we are cool to go because the net force on the object is mg and t. But then t is in an oblique direction. We can resolve it into horizontal and vertical component. Let's do that. So we have the horizontal component to be theta point in the direction of this component. We have t sine of theta, and this component being t cos theta, parallel to this component, which is also t cos theta, which is parallel to mg. So the equations involved in this system is we have t cos theta. Now let us recall that F is equal to ma is a vector equation. So it means forces in the vertical direction, you equate them. Then forces in the horizontal direction, you equate them. So t cos theta is equal to mg. That is the first of the two equations. And then the second one is t sine theta, which is in the horizontal direction, is equal to, in fact, it is the only force in the horizontal direction, but it is that force that gives the object a centripetal force, a prerequisite for the object to traverse a circular trajectory. So the centripetal force is equal to m v squared over r. Now we can divide equation 2 by equation 1. And if we do so, we have t sine theta divided by t cos theta. We have tangent of theta equal to, now we divide mv squared over r by mg. Now we have v squared over rg. Making v squared the subject, we have v squared to be equal to rg tangent of theta. The language of physics is mathematics, so let's read the physics into this. It means in this system of a bob and a string, that the object can traverse this circular trajectory of a radius r with a constant acceleration due to gravity, given that at every point on this trajectory, the tangential speed v squared is equal to that constant r times the g tangent of that theta it makes with the vertical. And so as the speed increases, what happens is r will increase, but then g is a fixed value. Theta will also increase. So whirling this at a higher speed, theta will start spreading. I mean, the whole system will start gaining a maximum theta. But the maximum is pi on 2, which is 90 degrees. It is a theoretical maximum. It can never reach that 90 degrees, by the way. So then, that is a requirement of the system, that the tangential speed squared is equal to rg tangent of theta. You cannot traverse this circular trajectory if v squared is not equal to rg tangent of theta. So if theta is 0, then v will be 0. If the radius of the circle is 0, it means you have not even set the whole conical pendulum into motion. And G cannot be 0, by the way. Okay. Now, next on the applications is a problem in physics that we call the loop problem. The loop problem is a ball. You know, this one looks like a roller coaster, but you leave an object here, then it descends this plane, and it takes a circular trajectory, then it descends away. Now, the problem happens to be at a point when the object has reached this part of the circular trajectory. So let's just say this height is so high enough that it has the energy, I've not talked about energy yet, to reach this point of the circular trajectory. Now at this point, the forces on this object is the force the track, this circular track, will exert on the bob. According to Newton's third law, this bob would exert a force on the track will exert equal but opposite force on it. Let's call that force T. And then gravity also acts on it, gravity mg. And this is the net force on the object, T, and then mg. We call it the loop problem because both forces are pointed downwards. But the question is, why is the ball not falling to the ground? It's able to make the bend and then roll away. So it turns out that T plus mg at this point of the trajectory is what gives it the centripetal force. Let's just call it ma, the mass times acceleration downwards. So T, which is the force the track exerts on the object, is equal to ma then minus mg. That is equal to m into bracket a minus g. So the follow-up equation is such that the force the track exerts on the object is equal to m into bracket a minus g. But it is a requirement of this equation that g cannot be greater than a. If g is greater than a, t will be negative. But you see, a track cannot exert a negative force on the object. So T has got to always be positive. For that requirement, G must always be less than A. So A must be greater than G at all times. Now, the problem arises when the object is able to make the bend. That is to say, T plus mg are both pointed downwards, but the object is not falling to the ground. The solution to this problem lies in the fact that this bob, before it reached this point, has got a tangential velocity to the circle at every point. So when it was here, it had that tangential velocity before it could climb. And when it climbs and reaches this point, it also has the same tangential velocity. So the bottom line is there is a tangential velocity to the circle. So this A, which is the acceleration of the bob towards the ground, though the bob is not falling to the ground. In fact, it is actually falling, except that downward acceleration doesn't mean it has fallen to the ground. It means that at a given change in time, delta t, the object has a velocity in that direction, which is equal to that acceleration time, delta t. So this downward acceleration provided by these two forces doesn't mean the object has already fallen to the ground. It is falling all right, that at every change in time, it has the velocity is equal to that acceleration times that change in time. but then it has already got a tangential velocity. Let me call the tangential velocity Vt, V sub t. So the case of the bulb at this point is such that it has got every infinitesimal time a velocity downwards, which is equal to that acceleration provided by these two forces, time delta t. But then in addition to that, it has got a huge tangential velocity at that point. So there are two velocities on the object, one downwards as a result of a delta t, and then one tangential, which it has already got before it can traverse this circular trajectory. So there is a net velocity on this, which is pointed in an oblique direction, like that. And that net velocity is pointed in an oblique direction. That demands that the object doesn't move downwards. It doesn't always move tangential to, but then it moves in a circular trajectory. So there is a tangential velocity like so. There is one provided by these two forces, and the net velocity is pointed not tangential to the circle, but in an oblique direction. That demands that it undergoes a motion around the scale. So it doesn't fly away, it doesn't move to the ground, but it traverses this circular trajectory at every point in time. So the lesson from this problem is that downward acceleration doesn't mean the object is falling to the ground directly. So if it has got a huge tangential velocity, then there will be a net velocity in an oblique direction. Next of the applications has to do with an object which is hanging. So there are two strings, maybe attached to a tree somewhere here. And these strings are holding this object in place. There is a force mg on the object, there is a tension T1, and of course there's a tension T2. Now these angles are known, theta 1 and then theta 2. And now the object is in equilibrium. Let's analyze this object. So what are the requirements for this equilibrium nature of the object? We can resolve T1 and T2 into horizontal and then vertical direction. So for T2, we have here to be T2 cosine of theta 2. Then we have this component to be T2 sine of theta 2. Now similarly, we have T1 cos theta 1, and then T1 sine theta 1. So still on the second law of Newton, which demands that vertical forces will be equal and then horizontal forces will also be equal. For the vertical forces, we have mg to be equal to, we have T1 sine theta 1 plus T2 sine of theta 2. Then for the horizontal forces, we have T1 cos theta 1 will be equal to T2 cos theta 2. Now, T1 is unknown, T2 is unknown, but then theta 1 and theta 2 are given. These are given angles. So they could be 45, 30, whatever. So the problem here is to find the tension, the two tensions, so that this object will be in equilibrium, given the mass of the object and then the gravitational pull. And you just have to manipulate this equation to get your answer. So theta 1 is known, theta 2 is known, M is known, G is known. The only unknowns are T1 and then T2. So with two equations, we can easily solve that. Now, you've got to have a test for your answer. That theta 1 will have to get a limit. Now, it has to be between 0 and then 90 degrees. So, the requirement of the equation is such that theta 1 cannot be 0. If theta 1 is 0, the string will be infinitely taut. Theta 2 can also be 0, or the string will be infinitely taut. You see, and then again, the theoretical maximum is 90 degrees. So that will be your test for theta 1 and then theta 2. It is now time to visit the problem of the century that every physicist, when he or she first goes into physics, fears the most, and that is inclined plane. It is a humor that physicists fear inclined planes because it dates back into history. Let's start with the inclined planes.